Thank you. It's independent of everything else I talked about. It's about this new construction of quantum LDPC code. It's a very significant breakthrough in quantum error correction from 2021 from Kalachev and Penteleyev. And until now, I hope I convinced you that we need quantum error correction, that you should work on quantum error correction because it's most of what a quantum computer do. In 10 years, when we're going to have big machines, it's going to be too late to build the whole architecture. We need to build it now. We need to have it ready, and there is a lot of things to do. We need to have decoders implemented in hardware. We need to have the code chosen. That's the first thing. And we are still discovering new code and better codes. So we need a lot of work. And the goal of this section is also to show you that there is beautiful math inside, and very modern math. It's actually about high-dimensional expanders that are still in progress today. We still don't have fully satisfying definition of high-dimensional version of expanders. And one of these constructions from Dinur, Lubotchev, and collaborators led to this quantum Tanner codes. So I'm not gonna give you any proof. I'm just gonna give you some pictures to get you some intuition on how we build these objects. And just to give you a brief review of the history of quantum LDPC codes. The first family of quantum LDPC code is Kitayev's code. They were not seen as LDPC code at this time, but they are LDPC. LDPC means low density parity check. So it's defined by its low weight checks. And we saw that they are defined by weight 4 checks, the toric code or the surface code. So they are LDPC, and they achieve a distance which is square root of n with one logical qubit. And for a long time, that was pretty much the best thing we could do. In theory, D can go up to n, and K can go up to n. So we would like to have K and D linear in n. There is still a lot of room for that. And classically, we do have that. We do have that, but it's also very easy to get that. We just take a random graph, and we take that as a Tanner graph, and we get a good LDPC code. We get D linear in n and K linear in n. So just random construction works classically, not quantumly. And after that, there is a construction a few years after that beats this square root of n by a tiny bit only, by a polylog factor, and still K equal 1. And for a long time, there was nothing better, and it was even proven that we cannot do better. D is upper bounded by square root of n divided by square root of K. So if K is constant, it's at most a square root of n. And you cannot do better. There is some assumption here. The assumption is that your code is defined by local constraints in a 2D grid. So if you have 2D local codes, they must satisfy that. You cannot beat the square root of n. And that's why Kitaev was stuck there.
Can I slow you down just a little bit, please? My name is Jens Pausberg. I'm from UCLA. So my question is, given that the square root of n is so central, could you just remind us of the intuition why it's got to be square root of n and not some other thing?
Oh yeah, thank you. So just to quickly review the surface code, we have this grid of, for distance 5, we have 5 by 5 qubits. Those are my physical qubits. And in general, it's D by D. So it's a grid of size D by D. And with that, I have a minimum distance D. And the logical operators correspond to a line of X or a column of Z. So the minimum distance corresponds to those weight of those operators that I cannot detect because they cross the lattice and they have a logical action on my code space. So this is why we have D, which is square root of the total number of qubits. And if I define any code on this grid of qubit, I put any set of check where I put a check and it is local, so it's acting on some radius R that is finite. It's a terrible ball. So it's acting on a finite radius R. You can define a large family of codes. There is many codes of this form. You will never beat the square root of n. You are bound by BPT, Parity Pool Integral. Thank you. Yes, and feel free to jump in. I have plenty of time because I have fewer slides less than yesterday, and I don't have a bonus section for the bonus section. Okay, and in 2009, we have this Tillich-Seymour hypergraph product construction. And there, we are still stuck at the square root of n. It's still a product construction, product of two graphs this time. But k is proportional with n. So we have many logical qubits instead of just one. And it's very significant. It makes quantum LDPC code better than surface code. Now we know it with, over the past few years, it took more than 10 years, but we designed circuits, layout, decoders, and now we know that they do beat surface code with explicit constructions. So it's a very significant jump. And we are stuck there for a very long time. Another 10 years until there is this construction by Hastings, Ha, and O'Donnell, where they beat the square root. They are at a power which is better than the square root by a little bit. So at this point, there is some hope. At this time, before this construction, we may start thinking, is it just square root of n the best polynomial we can achieve? And this is an anomaly. We can achieve something of the form square root of n times polylog, but nothing better. And some people were working on bounding this and proving that we cannot beat the square root of n. There is many bounds in different settings, but now we know that we can do it. And the idea to do it is to have a product which is twisted in some way, and it's done through some geometric object. And this leads to a bunch of new construction. We know that we cannot stick with the Cartesian product. We need to twist it in some way to make sure we are not stuck with the square root. And it leads to the lifted product codes that were introduced before by Priatko and Kovalev. And this one is almost at n. And another construction is an improved version and more explicit version of this one that gets rid of the polylog. And this one actually contains already the family of good LDPC code, but they could not prove it. And a year later, we have the good codes. We have good quantum LDPC code from Panteleieff and Kalachev. And a similar construction from Dinur, Evra, Levine, and Lubotsky and Moses leads to locally testable classical codes that are also good. It's a result in classical coding theory. It's also a very significant result. We have also been waiting for 10 years to get that. And the same mathematical object, the same combinatorial object leads to both constructions. And this paper is also very well explained. This work of, all the work of Dinur in general, the recent work of Dinur on high-dimensional expanders. And Leverrier and Seymour proposed a simplified construction, a simplified explanation for this construction that I find also very easier to follow. And in addition to that, we have good decoders. At least in theory, we know that those decoders can achieve a linear distance. If you have a good code, but the decoder does not achieve the full performance of the code, so there's no point in taking a good code. And so it was an obvious question. We have good LDPC code. We have a new family of code. We need to design a decoder. And those codes are similar to classical expander codes. For classical expander code, one of the breakthroughs was that they come with decoders, with efficient decoders, efficient local decoders. And the same idea works in the quantum setting. So generalization is not trivial, but the same idea works. And because it was an obvious question, a lot of people work on it. And within 2 days, on the archive, you could see 3 papers. So now we have everything we need asymptotically in theory. The decoders are still maybe not good enough in practice. The codes are maybe not good enough in practice. We don't have even explicit examples. We would like to have more explicit construction, but we know that they achieve the optimal performance asymptotically. So there will be another 10 years of work to make all of that explicit and practical.
And so this thing with linear time is now, because K and N and D are sort of more or less the same thing at this point. It's just linear time in any of those.
It's linear time in N, so in any of them. Yeah. Yeah, we use N as a parameter, but here K and D are similar. Okay, so the object we use is called a left-right Cayley complex. So if you are familiar with expander codes, it's convenient to build them from groups, from the Cayley graph of a group, a graph built from a group. And here we're going to do the same thing, but instead of a one-dimensional graph, we need a two-dimensional object. So we need vertices, edges, and faces. And that's why it's called a complex. And left-right, because it depends on left and right multiplication of the group. So we take a finite group and two subsets, A and B, and we are going to ask that the subset contain a set of elements and their inverse. We're going to come back to that later. And what we get out of that is a complex. So we need vertices, edges, faces. And what are the vertices? They are obtained by taking two copies of the group. So for each group element, I have two vertices, one with an index 0 and one with an index 1. And between these two sets of vertices, I have edges. And my edges are connecting a vertex with label 0, I'm going to call that a bit, maybe. So if the bit is 0, I multiply by A on the left, and I get a bit 1, and that forms an edge. So the left multiplication by A gives me an edge, and the right multiplication by B gives me an edge. And the bit changes each time I add an edge. And I need faces. So my faces are squares. And the squares are obtained by left multiplication by A and right multiplication by B. So I take an edge corresponding to A, an edge corresponding to B, and then I do both, left multiplication by A and right multiplication by B. I get 4 vertices, and if you try to draw it, it looks like that. So that was my first attempt trying to draw that. It's a mess, and I didn't take the right decision. I put the vertices with bit 0 on the left, bit 1 on the right. I was thinking it's going to look okay. But when you do it, you see that my squares here, so you have a square here, for instance, my squares are twisted. The sides of the square are in the middle. So let's try to do it. Let's try to look at the local structure a bit better. So we have three sets, one group, two subsets. Everything is finite. The vertex set is 2 copies of G. Edges are connecting the 2 copies. It's a bipartite graph. And the squares, they look like that. It's better. So we have 2 types of edges, one that we can draw horizontally and one vertically. So red and blue, or dashed and continuous, will be corresponding to A. So multiplication by A on the left is red, is horizontal. And multiplication by B on the right is vertical, and blue continuous edges. So I'm going to say type A and type B edges. So now we see a bit better. We have a bunch of squares, and edges are connecting between 2 subsets. Now, what is the neighborhood of a vertex? So if I consider a vertex V, what are the neighbors of V?
A1,
A. Sorry?
AG1 and GB1.
So AG1 and GB1. Okay, good. Thank you. So we have the vertices. Now, neighboring faces of this vertex.
Well, it's AG1, GB1, and AGB0.
Okay.
4, well, and G0. These are the 4.
Okay, great. So each time we take an A and a B, we can build a full square. So each time we take a pair AB, we can build a full square like that, a full face like that. Okay. So what does it look like roughly? An abstract representation is to say it looks like that. So f of V, it's going to be the set of faces that are incident to the vertex V, and it's indexed by the Cartesian product of A and B. So let's think of it like that, as a square, and my faces are the faces here. Now, what is the intersection of two neighborhoods? Let's say I have two vertices, one with bit 0, one with bit 1. And how do they intersect?
Well, it's a question of whether you can conjugate G prime, multiply by left and right G prime to get G, right? Am I saying it wrong?
Yeah, so let's say that they intersect in a non-trivial way, then they must share an edge. So let's say we have two vertices that share an edge. In this picture, that means that my first claim, so why do they share an edge? I told you that they share a face first. I assume that they share a face. For sure, we are guaranteed that they share an edge. But they could be here and here. They share a face. But yeah, I am assuming.
One is 0, one is 1.
0, and 1 is 1.
Okay, good. So if they were diagonally opposite, they will have the same bit. Okay, so they share an edge. Let's look at the case where they share a type A edge. Then we have two vertices of this form. What are the faces that they share? What are the faces that contain both V and V prime? So for every, So for every B, we have one, right? For every B, we can build a face from these two. So they look like that, and in the picture, they look like a column. What do you think is the case for type B edges? If they share a type B edges, it's going to be a row. Okay. So now we know that the intersection of those two things are either a row or a column in our square picture. Now I need an additional object. I need a classical code, a specific type of classical code. It's called a tensor code. I take two classical codes, and I'm the tensor code of two classical codes, C1 and C2. So those are defined by a set of checks on bits, another set of checks on bit. And the tensor product, it's a code with length n1 times n2. So the length is the product of the lengths. And I can interpret this vector or this bit string as a matrix. I'm going to put the bit in the shape of a matrix of size n1 by n2. And each column will be a vector of C1. And each row is going to be a vector of C2. So you have constraints on columns and constraints on rows. Basically, sorry, go ahead.
So does that mean that the matrix, when you multiply it on the left by some vectors, it's 0, and by the right by some vectors, it's 0?
So not exactly. Maybe, but at least it's not like that I see it. So that means I have a bit string, and I have some checks for C1, and I'm going to apply those checks to all the columns. And I'm going to apply my check of C2 to all the rows. So maybe it corresponds to your definition. It's a linear function, yeah. I'm worried about the size of those matrices. So check matrix is small compared to n1 times n2. Maybe I'm not understanding exactly what you have in mind. But yeah, there is many ways to define it. The way I see it is that maybe I'm going to give you an example.
Well, I'm just saying, if a check is to say that a dot product with some vector is 0,
yeah,
then you just dot, right? When you apply a matrix to a vector, you're just dotting all the rows or whatever with that vector.
Yes.
So therefore, to say that all the rows are checked is to say that when you apply the matrix to a column,
okay.
it's 0.
I see. Yes, exactly. So you have a
Left is for one and right is for the other.
exactly. So you can take the parity check matrix of this code and you can apply it to a column, or the parity check matrix of C2 and apply it to a row. Yes, that's right. Thank you. So if we take our Hamming code and a repetition code. So the repetition code has two code words, 0, 0, 0, or 1, 1, 1. It's a distance-free repetition code. And this code word, tensor bit 111, is going to give me this code word. It's a code word with length 7 times 3, so I'm going to put it on the form of a matrix. And you can check that each column is in the repetition code, and each row is in the Hamming code. This is a valid code word for the Hamming code. So they look like that. Those generate the code space. Okay, and we know the parameters of this code. So the length, the number of bits, of physical bits is n1, n2, and the number of logical bits is the product of the logical bits of these two codes. So we know how to count them. Now, based on that, we have two objects. We have our left-right Cayley complex, and we have our tensor codes. We can build the quantum Tanner codes. And remember that it looks like that locally, the neighborhood of a vertex. So our input is our complex and two codes. We're going to take two codes, CA and CB, and the code length will correspond to A and B. So we can think of a code word for the tensor code of these two as bits inside those faces. It's going to be the same. It's designed for that. Now we're going to place a qubit on each face of the complex. So each of these faces contain a qubit, and we need to define X checks and Z checks. So to define an X check, I take a vertex, I take a code word in CA tensor CB, and I define an X check given the code word. So when I have my vertex V, I'm going to look at the neighborhood. It looks like that. I'm going to place a code word for the tensor product of these two codes, for the tensor code. So you have zeros and ones, and each of the one I replace by an X. I get a X operator like that, acting on qubits, because qubits are on faces. And now, do you know I'm going to do a Z check?
Some zeros. It's one flip one.
You use B and the other multiplication.
So I'm going to use V. So I'm going to use the other vertices, so the bit 1. Okay. Then what bit string do I use? What 0s and 1 I put here? Same thing? So I want a constraint. I want to make sure that they commute. This X check must commute with my Z check. So if this bit string has odd weight, and I put an X check and a Z check, they will not commute. So how do I guarantee that they commute? I need to take a bit string that is orthogonal to this vector, right? Sorry? CB tensor CA. So we could try things like that for specific codes. We're going to do something slightly different. So if I want something that is orthogonal to a vector C, I'm going to take the orthogonal of this code, the orthogonal complement of this code. So I'm going to take it like that. And now, for each time I have a vertex with bit 1, I'm going to define a Z check. And I'm going to define it from the vectors of CA orthogonal complement, tensor CB orthogonal complement. And we saw that those two vertices, their face sets overlapped in either a row or a column. So when they overlap on a row, we will have a X that corresponds to a vector of CA and a Z that corresponds to a vector of CA orthogonal. So the two X and Z check will commute on a row. And if they overlap in a column, it's the same. So that's why we pick them like that. Now that proves the proposition. They commute because of that, because of this construction. Yes?
I'm a little confused. Where's the complement being taken in?
Where?
What are we taking the complement inside of?
Oh, so complements means it's a dual code or it's the orthogonal complement. So
What space?
In the space of code areas.
maybe I can review that quickly.
So in the vector space, wherever those codes live in.
It's like you make a matrix out of the null space of the other.
So a code, it's a subspace of Z2 to the n. We have a notion of inner product in Z2 to the n. It's the usual notion. Everything is mod 2. And if two vectors are orthogonal, that means that when I put x operator here and z operator here, they commute. Right? And C orthogonal is a set of bit strings in Z2 to the n such that x, y is 0 for all y in C. So it's all the bit strings that commute or that are orthogonal with the code C.
So is it easy to think of C purpose that all the checks that will be satisfied?
Oh, it's all the possible checks. So it's the checks, but additional things, like the code words. Yeah. All the checks are in C perp. That's true. Any other question about the construction?
So where's the group structure? Lost that.
So the group structure is giving the vertices. For each group element, you have a vertex, just like a Kelly graph.
It's moving these plaques, right? It's kind of, these big plaques are being moved as you...
Yeah, that's true. That's another way to see it, is that the group is also an automorphism. Each group element is an automorphism of the graph, because multiplying by an element will move one vertex to another. So it has a lot of structure and a very, very big automorphism group. Okay, so now the issue is that those papers, the goal of these papers is to prove that asymptotically there exist good codes, but there is no example in the papers. So I will try to build some examples to gain some intuition, and that's what I'm going to do during the rest of the hour. So I'm going to go through all these objects and slowly build a complex, and my goal was to recover the toric code. Can we recover the toric code as an example? Can we rebuild it to gain some intuition? So first I'm going to build Kelly graphs to make sure that we are all clear on what are these objects. So let's start with Z. My group is infinite in this case, but let's start with the group Z. And A is plus or minus 1. What is the Kelly graph of G equals Z with generator plus or minus 1? Sorry? A infinity. So in English, how will you say it? So what are my vertices? So I have, in a Kelly graph, I have one vertex for each group element. So what does the vertex set look like? All integers, okay. Now what are my edges? I see everyone doing that. Okay, so my edges are my group are given my group operation by adding an element of A. So it's either plus 1 or minus 1. So it gives you something like that, right? It's a line. It's a line where integers are connected. Okay, let's do more fun examples now. What do you think this one is? A square grid. Okay, that's a square grid. So the vertices are Z2. That's my black dots. And I connect by plus or minus 1, 0, or 0 plus or minus 1. So each vertex is connected to 4 elements in A. 1, 2, 3, 4. So the degree is the number of elements in A. What about this one? Okay, everyone sees it? So we added those generators. So we added 2 vertices around each, 2 edges around each vertex. So from this one, I added plus 1 or minus 1 minus 1. I should get that. What about this one? Z mod 8.
It's a circle. Goes in that.
Circle, it's a star, right? It's some kind of a star.
A circle or a star?
Complete graph.
So what is the degree?
2.
Degree 2. You have 8 vertices. So it should be a loop with 8 vertices. Good job. Right? So I start with an element. I reordered the vertices. It's not 0, 1, 2, 3.
Oh, if you reorder, but if you don't, then it's a star.
If I don't, I start here. I add 3. I add 3. I add 3. And I will do a whole loop. So I reordered them. I was lazy to draw the... Okay, you were both right. So why do we need a minus 1 equal A and B minus 1 equal B? Exactly. We don't want oriented edges. We don't want directed edges. So we are just going to assume an edge goes both ways. It's in our definition, we have a second generating set. I didn't use it here. That's true. Yeah. Sorry? So we could orient them or not, but in our code, we only care about a qubit placed on an edge. The orientation does not play any role, so let's forget about it. But we could orient it. We can also define a Kita-F code on a non-orientable manifold on the projective plane, and it does work, so orientation is not needed. Yeah.
The second line, the last element, do you mean plus minus parenthesis 1, 1? Second line.
Yeah,
Last one.
the signs are correlated, right?
The signs are correct.
So it's +1 or -1 -1. That's what I mean. So it's only in this one or this one. If you add +1 -1, you will add those. So what is a double cover now? So a double cover, it's a standard object in geometry. It's what allows you to go from non-orientable to orientable, from the projective space to the torus. And we can do it with a graph. So if I start with so in the case of a Cayley graph, I will take two copies, one indexed by 0, one indexed by 1, and it's what you call a double cover. And I have two types of edges. Each time I have my multiplication in the Cayley graph, I change copy. So I move from one copy to the other. And for example, let's look at the double cover of this Cayley graph. So first, what does the Cayley graph look like?
Z1, 2.
I mean, with the double cover, right?
Even things and odd things can, I mean,
Even numbers.
Two lines. Okay, I did not draw it this one, so I'm gonna add it here. So the vertices are integers, right? And then my edges are connecting with plus or minus 2. So I do that, and I keep going. And I have another set of vertices disconnected that looks the same. Okay, now when we take a double cover, what are the vertices? Agreed? Two sets. So it's this one, but I have two copies of my vertices. So I have G times 0 and G times 1. Where are my edges? Okay, I see that. Okay, so it looks like that. Each time we move with plus or minus 2, we change copy. So it looks like that. And this is the object we use to build the Cayley complex. This is the underlying graph. Okay, now we can move to the full complex. So let's do a first example. Here, again, it was an attempt to draw it as a bipartite graph with 0 on one side, 1 on the other side. But I could not see much with that. The squares are here, and it's a big mess. And it's for the group Z6. And also, I want to recover the toric code. For the distance-free toric code, I have 9 vertices, so I would like to have a group with size 9. So let's start with the simplest group with size 9. And my generators, I took the simplest one. I didn't want to take twice the same set, otherwise it's a bit buggy. But if I take two different sets, so if I take just G with one of the set, what do I get? What is the Cayley graph of GA? A circle. What is the Cayley graph of GB? Another circle, yeah, a different one. Okay, so let's do horizontal edges correspond to A. So it's plus or minus 1, and we flip the bit. And vertical edges correspond to B. It's plus or minus 2, and we flip. Now, if I start with 0, I have the neighbors are plus or minus 1 and flip. So the second bit is a 1 everywhere. And here it's plus 1 and minus 1 mod 9. Or plus 2 and minus 2 mod 9 vertically. And I try to keep drawing the neighborhood. until I see no more new vertices. Okay? So I stopped at this point, because here I have everything. So everything I see at the next layer, I have seen it already. So I have all the vertices, and I have even multiple copies on the side. So what I can see is that on the top side here and on the bottom side, I see the same thing. My vertices are the same, 6, 1, 5, 1, 4, 1, 3, 1. So that means this. What is this object geometrically? For now, we can fold it, we can identify it. What do you think is the whole thing?
Okay, I have a question. Why
It's a torus?
Why is the tree one there as well? So like we have
Yeah, so that's an issue here, right? It's a bit different. I should see 6, 1, 6, 1. They don't match.
Well, it's a torus twisted by whatever relabeling we have here.
Okay, you're going too fast. Yeah, it's true. So it's a torus, but we have to. So when I look at this vertex, 6, 1, it's going to be identified with this one. And this one is identified with the next one. 3, 1 is identified with the next one. So we start with an identification of the torus. It gives us a cylinder. And then we are about to glue it. But just before gluing it, we're going to shift it and glue it. So it suggests maybe it's not a fully satisfying example. I want the same torus as Kitaev. And
You don't have a drawing of that?
sorry?
You don't have a drawing of this?
I don't have it, yeah. I knew you could visualize it. So, and it's because I didn't take the right example. I should have taken this one.
So, in this case, you ended up
with suggestion earlier before asking the question.
Oh, sorry. Yeah, my name's Ahmed, by the way. Yeah. So in this case, you ended up with like one connected component, right?
Yeah.
Previous example, you had two. Is there any actual consequence for that, like physically?
I mean, it depends on the generating set. If you have two connected components, that means you can get rid of one of them and build a code only on one of the components, and you will get a better code because you will have two codes that are independent from each other. So maybe it's not a good idea.
2 qubits or something.
Sorry?
Trivially, you just have like 2 qubits instead of 1. So.
I have two codes. So it's like if I say I'm going to encode my information into 2 repetition code. I'm going to use a repetition code with distance 3 and another repetition code with distance 3. So my codes will be like that. Oops. Okay, let me try again. Okay, so if I build a code like that, do you like this code? It seems like it's not the optimal thing to do when you have 6 bits, right? You should have at least one check that connects both parts. So that's what you're going to do. And that's happening when your generating set are not generating the whole group. So you cannot reach everything from one vertex. Yeah. So it's not an issue. The construction still works, but it's maybe not the best idea to build good code. Oh, yes?
Hi, I'm Zane. You mentioned earlier that there was some bugginess if you choose A and B equal, and there was a footnote earlier that says you don't want AG to be GB, and I'm wondering intuitively if this seems to have something to do with the properties of the code. But one, is it easy to find subsets with that property, and two, sort of what does it mean for the context?
Yeah, it's possible to find sets with this property. Easy, I don't know how easy it is. But the issue is that in the construction, I'm going to get back a little. So in the construction, we start with AB and with 2 codes. And the code lengths are chosen so that each code word here fits in this square grid. If you don't have good properties like this conjugation, it's called total non-conjugation property, then you may have some vertices around which you have a smaller grid. You reach twice the same vertex in a neighborhood. So you have a smaller grid, and that means your code is not going to fit anymore. So it's just to make sure that all the local neighborhood looks the same.
So if I amended this code size requirement to be some reduced size depending on the violation of this condition, would that?
Yeah, that's true. You could do that. You could generalize the construction and say, each time I have a local neighborhood, as long as it looks like a square matrix, I can put a different pair of codes there. That's true, that will be possible. I don't know what it will give you. I mean, in practice, it's probably very useful to have a broad family. Yeah. Yeah, maybe you should work on generalizing that.
That condition just says that you have no edges that kind of backtrack, right?
There is no double edges, yeah. But if you have a double edge, you are missing one vertex in the neighbors, so the local structure is different, and you get in trouble. So yeah, I told you I want a 3x3 torus, so I took Z9, and obviously it was not the right choice. If I want something clean, I should take this group. So now let's do the same thing with this group. And we're going to see that we get, so type A edges are +1, 0, flip. It's a three-dimensional thing now. And type B edges are the same thing for, oh, is this incorrect? So this should be 0, +1, and 0, -1. So it should be the generators of B. So we do the same thing. We start from 0, 0, 0, and all the last bit is fixed to 1 for all the neighbors, and either we do +1 or -1, mod 3. So +1 and -1 for the first component or for the second one. And we obtain this grid. When I have this grid, I stop because I have seen all vertices. And there, we have a proper identification. This vertex is matching the opposite vertex. And 1, 1, 1 is matching 1, 1, 1. So on both directions, we have identification with the opposite vertex. We don't need to twist our torus. So now we have our torus. That's the first step. We still need to build the code and to check that it's the toric code. So we have our torus, and we said, here is the code construction. Qubits are on faces. So the faces are given by a generator A, a generator B, and we take a square like that. These faces are actually my faces in the complex. They do look like faces in this torus. So it's a very simplified case. Don't keep that as in mind as the typical example. It's a very simplified example of a left-right Cayley complex. Then we have a check. Each time we have a vertex V with bit 0. So I put them in black, and the bit 1 are in white. So for black vertices, I have X checks. For white vertices, I have Z checks. And the neighborhood looks like that. If I look at all the faces and send them to a vertex, so it's those 4 faces. Because my group is simple. And now I want a tensor code to put on these squares. So I want a product of 2 codes. Which code do you want to pick here? Do you have any idea? It has to be a code with length 2. So there is not that many choices. So I'm going to give you, so it's a complicated question. You have 2 bits. What check do you want to pick?
There are 3 possible.
Sorry?
3 possible, right? I mean, you can check the first bit,
So there
the
is
second one, or both.
no check first.
Yeah.
So the no check is maybe not a good idea. So let's say there is 1 check. Now which one do you prefer? So there could be, I could do that and have another check maybe that does that. But we said it's not a great code, right? So I'm going to pick this one. It's a repetition code with distance 2. I'm going to pick this code for CA, and for CB, I'm going to pick the same code. It's basically the only non-trivial code with length 2. So I don't have much choice. And I need to, so my CA tensor CB, it has 2 code words. The rows must be in CA, and the columns must be in CB, which is also CA. So rows and columns must be bit strings of this form. And that means for each of them, I'm going to put X generators, X check. So for this one, there is nothing to do. It's the identity. And for this one, I put X, 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 X on the 4 placket, on the 4 squares. So it does look exactly like the toric code, right? And it is the toric code. The only thing we need to check is what do we get for Z checks. So for Z checks, we do the same thing with a vertex, the white vertices with bit 1. So let's take one here. The neighborhood is also 4 squares, so the neighborhood looks the same. And this time, we don't put CA tensor CB, we put CA perp tensor CB perp. What is CA perp? It's the same. It's a set of bit string that is orthogonal with that. So you cannot have a weight 1 bit string. You have only even weight bit strings. So it's the same code. It gives you the same tensor product. And that means instead of x, 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 you have z, 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 z. So they look like that, and they commute. They are supposed to, and they do commute. And we recover exactly the toric code. So that's the most complicated way I know to build a toric code. But at least we have an example. It's satisfying. And now one of the main questions about in this branch of quantum error correction is to build more explicit examples. We need small size examples of good codes, of good quantum LDPC codes. And we don't have any. But the conclusion of the story is, how do we get good LDPC code from that? Which group do I pick? Which code do I pick? I can tell you what they pick in the proof and what we would like to make explicit. So what they pick is PSL2 of FQ to the I. If you are familiar with classical expander graphs, it's the same group. So it's natural to try this one. It has good behavior. It's a Ramanujan graph. It is optimal in many ways. It's optimal for graph coloring, for many graph properties. And CA is going to be a random code. CB is going to be a random code.
And what generators do you take the obvious?
The generators are non-trivial. It's a non-trivial set. It comes from the Bruhatitz building literature, and yeah, I didn't include them here. And it gives us a family of good quantum LDPC code. That's the result of.
Sorry, but the A and B, you take the same.
A and B, I take 2 different random codes.
No, I mean the subsets of G, the
Oh,
generators.
yeah, A and B are the same, as far as I remember.
Can you, Marius, can you say something about what you're using? You're using the Ramanujan property, and what do you use from the random code?
So we don't use the Ramanujan property. I mentioned that as one of the properties we have for this calligraph usually. But the basic idea of the proof is to say, to spread globally a property that we have locally. We want to prove that if we have an error in a small region, if it is not a stabilizer, we can detect it. So if we want to build something undetectable and non-trivial, we need a large set of qubits. That's what we want to say to prove that we have a large distance, that undetectable problematic errors are large.
So related to expanders or not? Or are you using expander type properties? Or?
Yes, I'm coming to that. So locally, you build a tensor product of 2 codes, and tensor codes have a good property called robustness, which means that they can detect all small weight errors. So locally, you can detect small weight errors, and because you have an expansion property, if you have this detection, and you are going to use the expansion to spread the robustness to the whole graph. So that's the basic idea, which is very similar to the case of proving good expander code, good classical expander code, which is you have a small code that detects locally your non-trivial code words, and expansion is allow you to spread. If you detect one, there must be a few neighbors that are also detected, and it's spread to the whole graph. So it's combining the effect of expansion that spread the robustness, the local robustness of the code. Now the main question is, can you make it explicit? Can you remove the randomness and give us small explicit example? Because right now there is no non-example from this family that beats even hypergraph product construction that I showed yesterday. Yes?
This is Adam. When you say remove the randomness, do you mean like their proof is on some infinite family with a lot of randomly chosen codes? And are you saying that if I just pick one. I just pick two specific random codes and construct this. It's not going to be that good.
So when you can prove that you have that for a random code, what you do is that the expected minimum distance and the expected dimension is linear. That doesn't mean that if you take one instance, it has good property. You may not be lucky. And it's also asymptotic, which means that it's true for very large lengths. But how fast does this converge? If you take finite size, maybe your success probability to have good codes is very small. And that's one of the issues. We would like explicit construction for which we can have a lower bound that guarantees a distance. Because as we discussed, computing the distance is NP hard. You cannot compute it. So I want a family that is explicit, no randomness, and I want a guarantee that I have a large distance. And ideally better than the non-constructions. Yes?
What kind of factors go into the distance proofs?
Yeah, it's what I was just mentioning, is that the robustness of the tensor code of these two is going to spread to the whole graph thanks to the expansion. And it's very non-trivial. I'm saying it in 2 sentences, like if it's simple, but it took 20 years to prove it. So. And people had the intuition that we need high-dimensional expander for at least 10 years. So it's not that we didn't know we need to use this object. It's that there is a lot of properties. Even proving the robustness of codes is in general difficult. And can you give me small examples with, I'm even very generous with the length. You know, I tell you, can you give me something with length of the order of 10,000 or smaller? And I'm not aware of any explicit constructions. And that's my conclusion. So I do think there is a lot of beautiful math in your correction. Yes? Oh, sorry, I thought you had a question. Yes?
I know earlier I've only heard this based on discussions with people who are talking about stuff I don't understand, but there's a connection between quantum LDPC codes and locally testable codes that are classical. And I know that it's very hard, or at least maybe desirable, to get local testability for quantum codes. And I'm wondering what no-go theorems or work in that area might exist.
They are worth a lot. It's non-trivial results. So the same object allows you to build locally testable codes. The basic idea of those locally testable codes is that you are going to have a set of checks, and you want the checks to have themselves checks, so that you can check your answer locally, and those checks on checks look like so bit check and check on check looks like my x check, qubit, z check. So the structure is vaguely similar, and that's why the same object is used.
But this breaks down for non-obvious reasons. If you're
Sorry?
this breaks down for non-obvious reasons in the quantum locally testable case, if you wanted.
Oh, you mean why do we want local testability for quantum codes?
I know some people want that for like quantum PCP conjecture things, but I'm just wondering why it breaks down in the quantum case, if there was a nice.
Yeah, I mean, it's a natural property of error correction. You want to make sure that if you have so local testability is the fact that if you have an error with weight W, you are going to detect it W times. You have of the order of W checks that will be non-trivial. And you see that it's not the case with the toric code. If you have a string of errors, you are going to detect only the 2 endpoints. You would like to avoid that. And yeah, people seem to believe that it's a property of robustness that's useful even in physics. I'm not sure I can give you a good intuition for that. Yes?
Adam again. What's the relationship between these quantum Tanner codes and high-dimensional expanders? Because to me, when you say high-dimensional expander, high means, there's dimension 2, complexes, simplexes in the simplicial complex, whereas this is like a 1D expander graph that you're starting with?
Yeah, it's 2D. Here it's 2-dimensional, we have a complex. So it's the first of high-dimensional. By high-dimensional, we mean higher dimension than the usual, which is dimension 1.
So what you're saying is that you start with a 1D expander, and then we make this 2D complex, and that thing itself we consider to be a high-dimensional expander?
Yeah, so it's a bit hard to answer because I haven't told you what a high-dimensional expander is. I haven't defined them. And even if I try to define them, one of the issues is that to define expanders, there is 3 definitions. There is a definition based on the spectral gap, one about mixing distributions, and one about the size of the boundary. And those 3 coincide, they match, they are equivalent. In the higher dimensional setting, the main question for more than a decade was to have similar definitions of high dimensional expanders and to make sure they match. And now, as far as I understand, they have 2 definitions that match, and a third one that's still a bit independent. And by matching, they match up to some constant, so they don't fully match. And this construction is a high-dimensional expander for one of these 3 definitions. But sorry? So it's the one related to the size of the boundary. So we didn't talk about the spectral gap, and I didn't talk about mixing random walk. And if I remember correctly, but don't quote me on that, so the spectral gap and the boundary are equivalent, but the constant change. And the mixing random walk is a bit different. Or maybe But also even what you call a random walk is different. You need to walk in this complex in a way where you change dimension in your walk. So it's a different object. And I still don't know if they have a fully satisfying definition today.
Yeah, I mean, it's so the family of high-dimensional expanders that I'm familiar with comes, I think, from the spectral gap definition. This is like the Wygotsky work. So it's interesting because there's like recipes for explicit constructions there, and now we have a different type of explicit construction.
Oh, and they are very different?
Yeah. Well, I mean, superficially they're different, but it would be interesting potentially to match them up and see how related they are.
They are not based on this group?
I mean, the one I use, they're based on PSL D, and so one higher dimension at least, and you can go up into any number of dimensions and extract.
Okay.
Maybe what's special about your example is that it's a 2-dimensional complex as opposed to yours, which is probably much.
Well, in my case, I have a 2-dimensional expander, but I started with PSL3 over F4. But you can actually do it up at any degrees.
Yeah, maybe that's a good opportunity for you to build new quantum LDPC codes.
I mean, they might end up being the same thing. That might be equivalent. That would be interesting in itself.
Yeah, I suspect they will be different if you start with a different group. Yeah.
Any other questions?
What about decoders? So before, when you did your own constructions of codes, you were careful with the decoders, but here they disappear.
So yeah, I mentioned that there is decoders that are good. The basic idea of the decoder is to use expansion also in some way. So you are going to use expansion and look at the weight of the syndrome and reduce the weight of the syndrome. So the idea is that no, okay, I'm not going to draw anything. But basically the idea is that by looking at the value of a single bit, I'm talking about the classical case, think about the checks that form an expander graph. When I have a few bits that are flipped, I will see some checks that are non-trivial. And I want to reduce this number of non-trivial checks until there is no more non-trivial check. And I'm going to do that by selecting one bit that triggers more checks than if I flip it. So I will flip this bit. It's going to reduce the number of triggered checks. And I'm going to keep doing that locally. And this is the original expander code decoder of it's Spitzer and Spielman from about 20 years ago. And for these codes, we have a similar strategy where locally, so there is 3 papers about decoder that I mentioned at the very beginning. I don't know if I can. So locally, you are going to flip a small set of qubits to reduce the weight of the syndrome. You're going to do the same thing, but you cannot do it 1 bit at a time. So I'm going to show you the decoders. So the decoders papers are those 3 papers that appeared roughly in the same time. And they all use the same idea, which is adapted from Spielmann and Sipser. And yeah, locally, they will select a small number of qubits for which they will apply X error, and it reduces the weight of the syndrome until there is no more syndrome. Because of expansion, you are sure that you can locally correct, and when you are down to a syndrome weight 0, you didn't introduce an error. Yes?
So does it optimize how
Can you say
many?
something about yourself?
Oh, sorry. My name is Anika. So does it optimize? Does it optimize the number of flips you have to do?
So it does not. It's not optimal. So there is still a lot of work to do with decoders. And I will claim even that it's not practical, because even though it's linear, you need to look at many subsets of size of the order of 10. So if you look at a set of size 10, and you look at all the Pauli errors inside, it's 4 to the 10. It's about 1 million already. And you have 1 million configuration for which you're going to select one that reduces the weight of the error. So we need to keep working on improving this constant 1 million. And we need to achieve the full distance, exactly, as you're suggesting. This argument is not achieving the full distance. So maybe there is some work to do. And another thing is that I didn't talk about fault tolerance.
And how do you avoid, like, what if you flip something and you think it's correcting a bunch of errors, but it creates more in another neighborhood?
Yeah, sometimes it does. What's happening with the classical case, and we expect the same thing with the quantum case, is that what you look at is the weight of the syndrome. And this is time. So at my first step, I start with the weight of the syndrome is the number of non-trivial checks, the number of checks where I see a 1. So I start with some weight. And after, I'm going to select a subset of qubits and flip them. Apply a Pauli error that reduces the weight. So my weight goes down a little. That doesn't mean that the weight of the error itself decreases. So my weight is going to keep decreasing, sometimes a lot, sometimes just a little bit. And when I reach weight 0, the residual error is either a logical error, if I did a mistake, if my decoder failed, or a stabilizer, and I succeeded. So in the meantime, okay, I'm going to use the same color, but the weight of the error, it's a different weight. Maybe it's of the same order. I'm going to go a bit higher. So the weight of the error may reduce if I take the right decision, but it may also jump a little. Oops, I should be down to 0 here. So if it works, it does something like that. It may jump sometime when I take a wrong decision locally, but I'm going to correct it after. And we can have a guarantee that if the starting weight is small enough, then you cannot jump too high because of the expansion property. So you are sure that you are not going to go high enough. And the issue is when you reach the minimum distance. So if you reach the minimum distance, you may apply a logical operator. But if you can guarantee that during the whole algorithm, the number of qubits with an error does not go too fast, that you stay below the minimum distance, then you're going to correct successfully. Yes?
My name is Rui Zhe. I have a comment on using the high-dimensional expander to construct quantum LTT code. There exists some prior work by Teddy Kaufman and some co-authors that actually use the high-dimensional expander to construct trying to construct good quantum LTT code, but they can only achieve the distance slightly above square root of n. It's like a square root of n times log n to the k, where k is some constant. So that's a work actually appeared before the fiber bundle codes. Yeah.
Oh yeah, that's true. So it must be Evra, Kaufman, and Zemmour. Yeah, I could not cite everything. Sorry about that. There is many constructions that are missing. Yeah, I think so. This work that you mentioned was giving you a polylog factor here, like this one, but higher. Yeah, the first polynomial one that is better than that is a polynomial better than square root of n was this one. But there is a lot of work in between. There is 20 years of work. There is tens of papers, hundreds of papers.
Maybe one last question.
Hi, my name is Arfan. So this guarantee that you mentioned with these like corrections, is this like a probabilistic guarantee or like deterministic? Like we're gonna definitely get it, or like?
Oh, it's deterministic. Yeah, yeah, it's deterministic.
Okay. I was just wondering, okay, is it like how many? Like it depends on what an error model might be. Like if you have like too many errors or few.
So, an intuition, it's about expansion or curvature. An intuition is let's say that I see a set of points and I want to shrink. Okay, I'm gonna. So let's say I see those points and I want to shrink this region. What I can do is that I can cut here, and I'm going to get rid of this part. And because of the curvature, I have some information that's going to allow me to locally cut some region and shrink it. And we can keep cutting. But sometimes we're going to take the wrong decision. So sometimes I'm going to add this part. And expansion is going to guarantee you that if you have enough expansion, even if you take the wrong decision in some regions, there is another region where you're going to do a big cut that's going to help you and compensate for this one.
Okay, so that's a geometric like consequence of like. What?
Yeah, I explained geometrically here, but it's about the graph expansion. It behaves the same.